Welcome to Neuromatch Academy. My name is Michelle Johnson. I'm an associate professor at the University of Pennsylvania in the departments of physical medicine rehabilitation and bioengineering. I direct the rehabilitation robotics lab. Today I want to talk to you about an application of your deep learning, the deep learning algorithms within the area of neurorehabilitation, and I'm going to do it through a specific case study. This study is a part of a larger study that's funded by the National Institute of Health called Automated Assessment of At-Risk Infants. The study is in collaboration with my lab, which is the Rehabilitation Robotics Lab, the Children's Hospital of Philadelphia, and the Cording Lab in Bioengineering. Let me start with some background information. There are 15 million premature births each year worldwide, and we estimate that 5 to 10% of these children will be affected by developmental disorders. This essentially means that they'll have difficulty functioning in their daily lives as a result of the developmental disorders. The most frequent developmental disorder is cerebral palsy, which affects about 2.11 infant per 1,000 live births. Cerebral palsy is essentially results from some type of brain infarct or brain activity or brain interruption during the infant birthing process and can occur up to about 2 years old. In low and middle income countries, the prevalence is projected to be higher and almost double. It's important for us to be able to direct and detect early in the process whether the infant might be at risk for developmental disorders in order for us to maximize and capitalize on the brain plasticity that is happening during this critical period, as well as to maximize functional outcomes for these young infants by being able to intervene early. So there are existing clinical methods that allow us to do some detection, but and they actually have relatively good results. However, they tend to be quite qualitative, very expensive because they require a lot of training. They're insensitive to small delays early in the development. They fail to account for natural variability in infant behavior, and they're not always accessible in research poor environments. So our research goals are to try and identify metrics that are able to distinguish at-risk infants from those that are typically developing when they play alone by themselves, meaning, and when they play with a toy. And so can their behaviors help us distinguish them? So we're asking the question is whether machine learning techniques can help us to automate the stratification of these infants. So our approach was a big data approach. We decided that we needed to develop a database of normative infant movements, and that we needed to also develop a database with the infants that we wanted to test in the clinical setting. And our goal then would be to compare and develop some type of algorithm that would allow us to compare their risk. The work that I'm presenting today has been pre-released in a preprint on BioRviz if you're interested. So how do we go about curating the normative infant movement data set? So we went to YouTube, we searched using key terms that were 1, 2, 3, 4, 5, 6 months old and N week old. We sorted through videos in order to figure out whether these videos were usable or not. We were looking for were the infants non-occluded, were the infants moving independently in the video, were the infants in the frame, were the videos at least 6 seconds. We were able to find about 385 videos, and we then also, once we parsed these, we were able to identify a good set that we could use for the training algorithm. The mean duration was 39 seconds. How did we then collect the clinical data? We had to use, we developed actually a special process to being able to do that. We used our play and neurodevelopment assessment gym that was developed in the Rehab Robotics Lab. Our goal, this gym consists of 3 main areas: the mat, which is sensorized here, and there are 4 sensors at the end that allows us to collect the center of pressure. Then there are mechatronic toys that are suspended, typically one at a time, above the baby. And then we're also collecting vision data, video data from GoPro cameras that are suspended, mounted specifically at the top and at the side to capture the baby's movements. Here's an example of a video that was collected from the clinical data set with the baby in the no toy condition. And we were able to then capture the baby's movement. Here's an example of the video collected with the toy condition. And as you can see in the toy condition, there is a little bit more obstruction that we need to deal with because of the toy. The average trial was about 199 seconds. Infants were specifically included in our data set if they couldn't walk, they had an absence of cardiac, neurological, and orthopedic conditions, and their parents had to have given us consent. So just to recap quickly, the normative data set, we've gotten this, but we need to parse it in another way. We were able to classify 103 YouTube videos and verify, and our clinicians verified that these infants were indeed typically developing. They also assessed probable age of the baby. We ended up using 103 YouTube data to do training, but included 85 that were in the assessment process that were age matched. In the at-risk infants, we had to go through the process of labeling their risk. So we use the Bailey Infant Neurodevelopment Screener, and this is a typical clinical tool that has been used in the past to assess neuromotor risk. The labels were, we had 19 infants, 5 were low risk, 5 were labeled high risk, and 9 were moderate risk. So again, we're asking, can we use ML techniques to automate this assessment process and to classify risk? So our focus is on the no toy condition first, because that's clearly easier than the toy condition, and that we hope to do in the future. This is our pipeline. As you can see with our pipeline, we took the data set, we had to kind of process the data in order to extract the features. Our essential process was that we annotated partial videos. We then adapted and retrained our open pose algorithm with the labeled data. We fit the pose to the full video. We then extracted the movement features from the pose and then compared the data set using a Bayes surprise algorithm. I'm going to walk through this pipeline individually. So the first thing is we used computer vision based pose estimation to extract the infant pose from the video. The algorithm of choice was the open pose algorithm that was developed by Carnegie Mellon. This algorithm uses convolution neural networks, and the concept and the idea is that it would use heat maps to identify 18 targets and also to look at the nose, to find the nose, the neck, the ears, the eyes, the shoulders, etc. And then it used part affinity fields to determine whether these, was it limb, was it connected or not, was it a part of the same person's body, and then it would result in these 18 targets with appropriate connections as it determined. OpenPose initially provided really messy estimates for our infants. We first started by using the algorithm straight off the GitHub site. And what we discovered was that this algorithm was trained for the COCO dataset and the MP2 dataset. And because of how it was trained, it wasn't able to accurately detect the infant body proportions, which are different from the adults. And so as a result, we needed to retrain our algorithm. So how did we do the retraining? So first we annotated 10 seconds of 103 YouTube videos and the first 30 seconds of the 19 clinical videos. We then looked and identified and labeled the key points using in 1 in 4 frames, and then we labeled them manually with VADIC. We ended up with 8,003 frames in the training set and 1,036 frames in the validation set. We then trained the algorithm with a gradient descent. By the time we're done training, 75 iterations later, we were able to get the RMS error down to something that we believed was indeed reasonable. So this is the video of our network trained the network trained video, and you can see that it's doing a pretty good job assessing the baby's motion and tracking the infant's movement. As you can also see, the 18 features that were resulting, the ankle, the elbow area, the shoulder, you can see then that we, from this, could be possibly able to extract the movement of the baby and even some angle information. So we had to then clean the data that resulted from the open pose. The process was removing outlier, interpolating, and the drop for the drop points, and anything that so we interpolated for those missing markers, but we also had to drop points that were greater than 2 standard deviations. We use a smoothing process using the moving average filter. We had to deal with the fact that we were collecting all this video with different cameras, so we dealt with the fact that we had possible camera movements by using the trunk as our reference body part, and then normalize the lengths of critical lengths by the trunk length. Here is just a figure where you should, so we can see the position data, for example, for key body parts like the ankle and the wrist, left and right ankle and wrist. And we extracted from the open pose data kinematic features such as the absolute position and angle, variability in the position and angle, mean speed, velocity, acceleration, correlation, as well as entropy. And we pre-registered our algorithm before we went ahead so that we would maintain the integrity of the data. Here is a look at what the different feature plots. And as you can see, we have already, you can kind of see that the features are beginning to stratify visually. The normative data is in gray. The low risk infant data is in green. The moderate risk is in blue, and the high risk in red. We had some specific intuition clinically. We anticipated that the at-risk infants or the clinical data might move a lot slower. And that their movements might be more stereotyped. And as you can see from this data set, we're beginning to kind of understand a little bit of that, but it's hard to actually visually separate the baby, so the infants from each other. So this is why deep learning was important. To compare the infants in the clinical setting, we used the naive Bayesian surprise metric, which assumes normal distribution and feature independence. The normalized metric, so we get a normalized metric with respect to the normative database. So we get and it estimates the log probability that an infant's movement are drawn from the normative distribution. And as you can see, some of the equations are listed here. So what do we end up with? We ended up with the probability of whether our low-risk infants were associated with the normative group, and we get a probability for the moderate risk and the high risk. As you can see, the algorithm actually does a really good job of separating out the high-risk infants from the normative infants, and that actually was significantly different, but not such a good job separating the moderate and the low-risk infants from the normative data. So this suggests that we either need more data or we might need to examine critically our features to see if we can improve which features we use to support this prediction. So in the results, the question is, we asked ourselves is, can the infant behavior be used to classify level of impairment? And the answer would be yes. So this, you could argue, is an example of the encoding process, where we're looking at external behavior and we're trying to predict something about the brain state. We were able to predict somewhat the movement and relate the movement to the level of impairment in terms of risk. We weren't able to do it as well as we wanted to. We clearly were able to separate out the extreme, but the algorithm needed some work in terms of low and middle risk infants. So the implication going forward is that we're able to then possibly develop interventions that automatically stratified infants, and that we need to improve our CNN prediction when obstructions occur in the video is now our next step. So in looking at the toy videos, we will want to be able to identify more complex interactions with the baby. And as you can see, the obstruction or possible obstruction of the toy would prove challenge to the open post process. So as you can see, some of the interactions that we're looking for would be the babies touching with their hand engagements. Then we're looking for the feet, engagement with the toy with the feet. And then we're also trying to look at involuntary data. So the next process in the algorithm is developing maybe a more sensitive deep learning algorithm. Can it be used then to detect specific behaviors with the toy? And what we're hoping is that the current algorithm can be tuned. And as you can see, deep learning actually offers us a viable opportunity to examine infant motor behavior and clinical infants and be able to early detect their risk. Thank you for this opportunity to give you this lecture, and I hope that you could see the utility and the application of deep learning. Thank you.